Today's lesson is going to be on particle movement once again, and this time we're going to be using our graphing calculator to display the velocity and acceleration graphs. And I'll show you a special function of the graphing calculator that you can use if you're allowed to use a graphing calculator on a problem like this. What I'm going to need you to do is go gather, if you can, at least one ruler. If you have two rulers in your house, that would be great, because it'll help me show you one thing that I want to show. And then if you could have two colored pencils, green and red are the two colors that I'm going to be using. So if you have those two colored pencils, if you could grab them and your graphing calculator. So if you'd like to shut the video off right now and go gather these materials, you're going to need them in order to take the notes correctly that I'm going to show you on this page. So now that you've gathered all of the materials that you need, hopefully you did, what I'm going to have you do is draw some XY axes down here. So over on the left-hand side of your paper, just take your pencil and draw, and don't move your ruler for all three of these. If you could draw, there's one, maybe draw it, well, let's all do the same thing. Let's draw it 2 inches long here, and then go and draw the next one directly underneath it. I'm going to start at 2.5 and go to 4.5, so another 2 inches here. And I'll start at 5 and go to 7, so another 2 inches down here. So you've got 3, these are like your y-axes all lined up perfectly straight in a row. Oops, you didn't see what I was doing. So you got 3 of them here, all lined up in a row. All right, this first y-axis is going to represent the x of t, and this x of t is going to be in centimeters from the origin. That's what this y-axis represents. This second y-axis is going to represent v of t, and that's the velocity in centimeters per second squared. And then the last one is going to represent your acceleration, a of t, and that's going to be in centimeters per second per second. A lot of teachers call this centimeters per second squared, but it's really more appropriate to call it centimeters per second per second. So those are all the y-axes, all lined up perfectly above each other. Now I want you to draw the horizontal axes, and let's make these all the same length also. So let's go about halfway up here, and let's make these all 2 inches long. So I'm going to go 2 inches out here, and then go up to the middle of this, about the middle, and go 2 inches along here, along the velocity, and then down here under the acceleration. You can have your horizontal axis a little further up than halfway, because it's got to go down below. So we're going to draw this 2 inches also. And now we're going to, these horizontal axes all represent t for time, all 3 of them, and these times are going to be in seconds. Maybe I'll zoom it out so you can kind of see more what I'm doing here from above. And these seconds all have to line up with each other. And this particle movement, the particle movement function is going to be x of t is equal to e to the power of sine of pi over 2t, and that whole function is subtract 1 from it. So this is a complicated function that we could take the derivative of if we wanted to, but it gets a little bit messy because there are a couple of chain rules that have to apply. And then if we want to take the derivative of that, you're going to have a product rule in there with a couple more chain rules. So it gets very complicated when you algebraically find velocity and the acceleration of this given position function. So this is the position, and this is in centimeters from the origin, and t is for time. So the time goes from 0 seconds all the way up to 4 seconds. That's going to be the domain of the function. So the particle stops or starts when time is equal to 0, and it stops when the time is equal to 4, and the time is in seconds. And the x value is in centimeters. Centimeters from the origin. Look at here. All right, let me focus this a little bit better here. So since these horizontal axes are all 2 inches long, we can mark tick marks every half an inch to mark each second because we need to go out to 4 seconds. So every half inch, mark a tick mark. There's a half, a half, a half, a half. So this is t equals 1, 2, 3, and 4 seconds. Same thing down here with this velocity. Every half of an inch, we're going to mark a tick mark. So this is 1, 2, 3, 4 seconds, and then down on the acceleration graph, mark every tick mark half an inch. So we got 1, 2, 3, 4. So we got t equals 1, 2, 3, 4. And what we're going to do is we're going to use our graphing calculator to graph these. So pull out your graphing calculator. Oops. And I'll clear everything out here. And put in under y1 e to the power of the sine of pi divided by 2, and we'll use x instead of t. Close up the parentheses, and minus 1. So we're going to set our window to start at x equals 0 because this is our t value. The x max is equal to 4. I've already graphed this, so I'll just tell you that this y min doesn't need to go any less than -2, and the y max doesn't need to go any more than +2. And I think let's scale our x-axis. That's okay. We'll scale that by 1. So if you can set up your window on your graphing calculator like this, and then press your graph button, we'll see what the graph looks like. So what happens here is this function reaches its maximum point here at time equals 1 second, and its minimum point here at time is equal to 3 seconds. So let's take a look at our table of values. Our table of values, remember x is really t, so these are time equals 0 through 6 seconds. We are only going up to 4 seconds here. And this is the distance from the origin. So this particle starts at 0, 0, starts at the origin. And then at time is equal to 1 second, this is the maximum distance away from the origin, 1.7. So we can go up to 2. And I guess we'll go down to -2 on our x-axis. And when time equals 1 second, the distance is 1.7 centimeters. So time equals 1 second, the distance is equal to 1.7 centimeters from the origin. And then at time is equal to 2 seconds, we're back at the origin again. When the time is equal to 3 seconds, we're only down to 0.6, so you're only down halfway to the -1 down here. And then you end up at time equals 4, so you end up back at the origin again. So this graph, and this represents the distance. Remember, centimeters from the origin is what this represents. Now what we're going to do, instead of algebraically finding the first derivative, we're going to let our calculator do it for us. So press y equals and go down to y2. And if you press the math button, and then you go down to option 8, numerical derivative is what this and deriv means. So you're going to hit option 8. And we're going to tell our graphing calculator to graph the derivative of this. So with this box, you type in x, it's dy dx. And in here we're going to put the y function in, but you don't have to type that all over again. All you have to do is press the vars button. So press vars, go over to your y variable, option 1 function, option 1 y1. So what we're asking this calculator to do is calculate the derivative of what's in y1. And then this x, you could put a number in here, but if you put x equals x, it's keeping x as a variable. So what we're really doing here is we're going to be graphing dy dx and let our calculator do it. So let's go up here to y1 and unhighlight this equal sign because we don't want to see the graph on top of itself. We just want to see what the derivative looks like. So press the graph button and here comes the derivative. Looks like it's going outside of our window range, both above and below. So we'll just change our window. Let's hit the on button, press the window button, and let's go from -4 up to +4 on our y max and min. Press graph again, and then we'll get a graph of the first derivative. And if you'd like to algebraically calculate the derivative of that function, you can. And if you put that, what you calculate into the y3, for example, it should be exactly the same as this graph here. So we've got some important values on this graph here. Let's calculate the maximum. So second calc max, because when we calculate the acceleration, in our next one, we're going to want to get the local max, so we know where the acceleration will go through the x-axis. So enter, enter, enter. So what happens here is at time is equal to about 0.424 seconds. This is the velocity function, so it's 2.29 centimeters per second. And where does it start? Let's see. Well, let's first of all put in at x equals 0.4. Let's mark that on here, 0.424. At 0.424 seconds, the maximum goes up to 2. So we'll just go up 1, 2 to 3 here. And this is 2.3. So it's up to here. And let's calculate the minimum now that we're at it. So second calc min and go down. This will give us our local min. Bound, right bound, enter. So our local min at time equals about 1.6 or 1.576 seconds. The velocity is -2.3 centimeters per second. So this is about 1.56. And this goes down to -1, -2, -2.3 down here. So those are about the only two important things. Oh, we knew it was going to go through the x-axis at time equals 1 because that's where our local max is here, and our local min at t equals 3, we know it's going to go through the x-axis here. So now it's just a matter of finding out where these values are. So we got 1.57 it starts at time equals 2, we've got -1.57. At time equals 3 and at time equals 4, we're right back where we started, so it should be even here at time equals 4. And let's just see what our graph looks like so we can get kind of an accurate graph here. So it goes up, comes down, hits the minimum. And this is our velocity function. This is v of t, and this is in centimeters per second. And notice that the max here is where it goes through, and the min here is where it goes through the t-axis. So now what we're going to do is we're going to get a graph of our acceleration function. So hit y equals, and let's unhighlight y2. Just hit enter. We're going to do the same thing again. We're going to press the math button, math option 8. And then we're going to type in x in this box, and instead of y1, we're going to get the derivative of y2. So vars, y vars, function, y2, and we're going to have our variable be equal to x. So now this is actually the second derivative of our original function here. And I've already graphed this, so I'll just tell you that the window, the Y min needs to go down to -7 in order to see the whole thing. So just change your window so you can get down to that point. And if we graph this, here's the second derivative graph. And it's kind of slow because our calculator is doing a lot of work calculating all of the derivatives along the way between t equals 0 and 4, but it's a lot better that the calculator does it than we do it by hand. All right, so this is our acceleration graph. And the important points here are this t-value, but we've already calculated it. This t-value is 0.424 because the local max on here will be where it goes through the x-axis down here on your acceleration graph. So right directly under this max, we're going to put this x-intercept, which relates to that. And it looks like at time equals 1, it's pretty close. At time equals 1, it reaches the local min. And then at time equals 2, it reaches a local max, and at time equals 3, a local min. So what we're going to do is just take a look at our table of values so we can get some accurate numbers here. And like I said, this is the minimum point, this -6.7. It's pretty close to the minimum anyways, and these are pretty close to the maximums. So on our y-axis, we'll go up to 3 and down to -7. So let's go up 1, 2, 3. And down -1, 2, 3, 4, 5, 6, 7. And we know it's going through the x-axis here, and we know it's going through the x-axis at this 1.57. So just directly below this local min, we'll put our x-intercept. And other than that, we'll just plot these numbers. So 0, 2.5 approximately, 1, -6.7 down here. We know it's going through the x-axis here. And then at 2, we're back up to where we started from. At 3, we're going to 0.9, which is almost 1. At 4, we're going back up where we started from. So let's just take a look at this graph again and connect all the points so it kind of looks like the graph. So it's coming down, coming back up, coming down, and going back up. And this is our acceleration graph with a couple of key points here. And now the reason for our green and red pencils is everything that's above the x-axis or above the t-axis, let's just color those green. Green means go. Green means positive usually. So all the parts of this graph that are above the x-axis, just color those green. Excuse me. On all 3 graphs. And we'll talk about what all these things mean. Anything underneath the x-axis, color those red. So we've got red underneath here. We've got red underneath here. And we've got red underneath here. So up here, what does it mean when the position function is above the t-axis? I'll write it in here. Green means to the right of the origin 0, 0. And red means it's to the left. We haven't graphed this on the x-axis yet, but we will, of 0, 0. So this particle moves to the right of the left axis, right of the origin, and then it goes to the origin. Right here, it's at the origin again. Because it's at a distance of 0, it starts at the origin. At 2 seconds, it goes to the origin, and at 4 seconds, it stops at the origin. So there's 3 places where this particle starts, goes through at the origin. This is the furthest from the origin it ever gets, to the right, and this is the furthest to the left. This minimum point, and this is the furthest to the right. and the furthest to the right it gets is at 1.7 centimeters, and the furthest to the left, I think we said it's about 0.6 centimeters left. All right. So now, what do the green and red mean here? Well, if you have a velocity that's positive, it just means that the particle is moving towards the right. So green on velocity means particle moves to or towards the right. And red means particle moves to the left, which makes sense because when you're above the x-axis right here, it means the particle starts at 0 and it goes to the furthest to the right, and then once it hits the furthest to the right point, then it turns around and heads back to the origin again. And then it keeps on going past the origin, and then it goes to the furthest to the left when it hits down here, and then it turns right around and goes back toward the origin again. And we'll graph this movement on the x-axis. So that's what the red and green mean as far as velocity goes and the graph of it. And on the acceleration, what the green means is it has positive acceleration. Red just means negative acceleration. I'm not going to write those two things down because hopefully it's obvious from this graph. But why I colored these green and red is and why we need two rulers is this. When both velocity and acceleration are green, those time periods, it means the particle is speeding up. Particle speeds up when, which means, when means the time intervals, both v of t and a of t, when both the velocity and acceleration are the same color. And by the same color, it means they're both green or they're both red, and it means they're both positive or they're both negative. So if you take these two rulers, hopefully that you have, you're starting at t equals 0. And then if you look in between these two rulers, don't look over here, but if you look in between these two rulers, you can see that both functions are green. So we have a green velocity, a green acceleration, right up until we get to this point right here, which is the maximum point on here. So between t equals 0 and 0.424 seconds, this particle is speeding up. So it's just in this interval right here, from here to here, that the particle speeds up. From here to here, because both velocity and acceleration are positive. Then the acceleration becomes negative. So once you hit this, we've got a green velocity function and a red acceleration. So this is the slowing down period of time until you get to this point right here where the velocity turns negative. So right here, velocity turns negative, and what's happening to the acceleration at this point? The acceleration is also red. So we've got two periods of time starting right here at time equals 1 second, going all the way up until time is equal to 1.576. So in this period of time, the particle is also speeding up from here down to here, because both velocity and acceleration are red. And then when you hit time equals the 1.576 that we calculated, you can see that velocity is red, negative, acceleration is green, positive. So this is a slowing down period of time until we get to this point in time right here at time equals 3 seconds. And at 3 seconds, both velocity and acceleration are green. So we have a speeding up period of time here. So speeds up from here to here, from here to here, from here to here. So we can mark that down as far as interval notation. Particle speeds up between 0 is less than t is less than that 0.424 seconds that we calculated earlier. It also speeds up between 1 second and when it hits bottom down here, which is 1.576 seconds, and then it speeds up from t equals 3 to 4 seconds. So this is important, and it speeds up in these areas, and then otherwise they slow down. All right, so the last thing I'm going to do is we're going to indicate this particle movement on the x-axis. So let's draw an x-axis way down at the bottom, and we'll see where this particle is going. Here's our x-axis. Here's our origin, 0, 0. This moves to the right until it gets to that 1.7 centimeters away. That was the furthest to the right it moved. And if you remember, the furthest to the left it moved would be that negative 0.6 centimeters. So how does this particle go? It starts here at 0, 0. It moves to the right until time is equal to 1 second, and it's 1.7 centimeters from the origin. Then it turns around and starts moving to the left. Right? Particle moves to the left during the red period of time, so that's time is equal to 1 second all the way up to 3 seconds. And at 1 second, we were 1.7 centimeters away, and at 3 seconds, it was 0.6 centimeters to the left. So from here to here, the particle moves to the left, and this is at t equals 3. And then at t equals 3, the particle moves, turns around. Here's the turnaround point, right? It moves to the right, then to the left, and then to the right. So these are the turning points. And then it ends up right here at t equals 4. So it moves here, then here, then here. Well, what's the distance traveled? The distance traveled is 1.7 centimeters plus another 1.7 to get back here again, plus a 0.6 plus a negative 0.6. So you can get the total distance traveled just by doubling this 1.7 and doubling this 0.6. And that'll be about it after we calculate that. Total distance is equal to 2 times 1.7 approximately times plus 2 times 0.6. And let's just get our calculator out. I should be able to do this without a calculator, but I'm just too tired. So 2 times 1.7 plus 2 times 0.6, approximately about 4.6. Whoops. About 4.6 centimeters. It totally moved in 4 seconds. Well, hopefully this colorful presentation will help you understand particle movement a little bit better, and showing you some tricks you can use in the graphing calculator is also a nice thing. Have a great day. I'll see you on Friday or tomorrow, or hopefully I'll see y'all tomorrow.